Imagine a single number so vast that writing even its digits would require more space than every atom in the observable universe provides. Not a guess, not science fiction, a precisely defined mathematical object used in a real proof. What if numbers themselves could break your brain? Not by being hard to calculate, but by shattering our intuition about size, reality, and what big even means. Today, we confront numbers like Graham's number, tree, 3, and the busy beaver sequence, concepts born from rigorous mathematics that expose the limits of human comprehension and the physical universe. These aren't abstract games. They emerged from legitimate questions in combinatorics, Ramsey theory, and computability. Stick with me as we journey into realms where even the universe is too small. If you're new here, hit subscribe and turn on notifications. We're diving deep into facts that will rewire how you see reality. Let's begin. Numbers have always challenged humanity. From ancient tally marks to Archimedes estimating sand grains in the cosmos, we've pushed boundaries. A Google, 10 to the power of 100, or 1 followed by 100 zeros, was coined in 1920 by 9-year-old Milton Serrata. A Googleplex, 10 Google, dwarfs it further. By the 20th century, mathematics formalized infinity and enormous finite quantities. Ramsey theory, developed in the 1920s to 1930s, explores order in chaos. In large enough structures, patterns must emerge. Ronald Graham, a mathematician and juggler, worked in this field. In 1971, Graham and Bruce Rothschild addressed a hypercube coloring problem. The smallest dimension n, where 2 coloring edges, guarantees a monochromatic planar K4. They proved bounds existed. Graham's upper bound became legendary. Meanwhile, computability theory, rooted in Alan Turing's 1936 work, asks what machines can compute. Tibor Rado's 1962 busy beaver problem measures the maximum steps, or one's a halting end-state Turing machine produces on a blank tape. Simple rules yield explosive growth. These ideas sit at the intersection of pure math, logic, and physics, revealing how abstract numbers outstrip physical reality. Graham's number, denoted G64 in Knuth's up-arrow notation, starts with G1 equal to 3, a power tower of 3's iterated immensely, and recurses Gn equal to 3n minus 13, up to G64. Even its digit count defies the universe. To write Graham's number in decimal, assuming 1 digit per Planck volume, smallest measurable space, you'd exhaust the observable universe's volume long before finishing. And this holds for iterated digit counts too. Tree 3. From Harvey Friedman's work on Kruskal's tree theorem, finite forms dwarfs Graham's number. As mathematician Tony Padilla noted, Graham's number is effectively 0 compared to tree 3. It counts maximum trees with 3 labels under embedding restrictions. Busy beaver numbers BB5 equal to 47,176,870 steps, verified in 2024 by the Busy Beaver Challenge using proof assistance. BB6 exceeds towers like 10 to the power of 10 to the power of 7, or higher, linking to undecidable problems. These are verified through peer-reviewed proofs and computational verification, not speculation. Early 20th century mathematicians grappled with infinities. Georg Cantor distinguished countable and uncountable sets, but finitists like Gauss protested completed infinities as improper. Ramsey theory advanced with Frank Ramsey's 1928 theorem. Graham's 1971 paper gave a massive but improvable bound for the hypercube problem. Martin Gardner popularized a related enormous number in Scientific American, 1977, cementing public fascination. In computability, Rado's Busy Beaver highlighted non-computable functions. By the 1980s to 90s, BB 4 equal to 107 was proven. BB5. Lower bounds grew via exhaustive search. Physical limits loomed. Information in the universe. Bekenstein bound can't store these numbers' full descriptions. Tension built. Math demanded precision. Yet reality couldn't contain the answers. In the 1970s, Graham refined his bound to the now famous G64 sequence. This upper bound, though vastly larger than needed, later improvements exist, entered Guinness World Records, 1980, as the largest number in a mathematical proof. The pivotal shift, recognizing that finite but incomprehensible numbers arise naturally in legitimate proofs. 3 later emerged in Friedman's work, showing even greater scales. For Busy Beaver, the 2024 verification of B5 marked a community triumph, using CAQ Proof Assistant after decades. These moments revealed math's power. Rigorous logic produces entities beyond physical instantiation. As John Baez noted, storing Graham's digits in your brain might collapse it into a black hole. An underestimate. Subscribe for more. Let's continue unraveling these truths. Debates persist on exact values and implications. Graham's number is an upper bound. The true minimal n for the hypercube problem is between 11 and 13, or higher per some bounds, but small compared to G64. 3 and larger numbers like SSCG 3 are accepted as vastly bigger, but exact computations remain impossible. Busy Beaver values beyond B and B5 connect to open problems like Collatz or Riemann hypothesis via halting machines. Some may be independent of ZFC axioms. Experts distinguish. These are well-defined via formal systems, but non-computable. Misconceptions include treating them as infinite, they're finite, or physical objects. Public reactions mix awe and skepticism about relevance, yet they illuminate Gödel's incompleteness and computability limits. Uncertainty is clearly documented in peer-reviewed literature. Picture Ronald Graham, not just a theorist, but a performer who juggled and did backflips. His work yielded a number embodying humility before mathematics' vastness. Graham's number isn't arbitrary. It's a beacon in Ramsey theory, proving order emerges amid complexity. The emotional reality, humans, with brains holding approximately 10% to the power of 15 connections, confront entities where even iterated descriptions fail physically. Trying to grasp 3 forces surrender to abstraction. A documented quote from Graham's era captures this. Mathematicians like him navigated a bound so vast that it redefined records. Consequences ripple. These numbers test physical information limits. The Bekenstein bound caps data in any region. Graham's exceeds it for the observable universe. Busy Beaver machines link to undecidability, proving one halts could solve millennium problems. Unexpected humanity shines in the Busy Beaver challenge. Amateurs and experts collaborated online, verifying B5 after 40-plus years using open tools. It reflects curiosity's persistence, people devoting time to pure knowledge, echoing Ramanujan's intuitive leaps or Cantor's infinities. Well documented. Last digits of Graham's number are known 2464195387. B5, exactly 47,176,870. These aren't myths, but archival mathematical records from journals, Wolfram MathWorld, and verified proofs. They humble us. The universe is finite. Math transcends it, revealing our place in a structure of logical necessity. The anchoring idea of unimaginable scale evolves, from Gödel's playfulness to Graham's proof-bound terror, to Busy Beaver's computational abyss, showing intellect's reach and limits. These numbers reshaped perceptions of scale in mathematics and physics. Graham's popularized Gödelology, tree, 3, and successors advanced proof theory. Busy Beaver results fuel research into axiom independence and AI-assisted proofs. Culturally, they inspire awe in documentaries and books, reminding us of humility. Lessons. Rigorous formalism yields surprises. Intuition fails at extremes. Collaboration solves hard problems. They influence computability, complexity theory, and even philosophy of math, affirming abstract objects' reality within formal systems. Legacy endures as tools for exploring boundaries, with ongoing work on higher B and B, N, and related functions. Numbers like these force us to confront how much of reality lies beyond our physical and mental grasp, yet remains logically true. They affirm math's beauty and terror, precise, verifiable, yet mind-breaking.